All right. So let's have a look at in terms of electroplating. If you want to electroplate the element, let's say for example, you take a spoon and then you want to cover the spoon with silver. So in your solution, you'll have silver solution. You'll have silver solution. All right. And then your electrodes also. The electrode connected to the positive terminal will also be a silver electrode. All right. While the electrode connected to the negative terminal will be the spoon. I'll just draw it like this. That's our spoon. What we want to do is we want to cover this spoon with silver. That is why we connect this on the negative electrode so that it can receive electrons and it can be coated with silver. All right. So in the case like this, what you are having is for your oxidation and for your reduction. Your oxidation, let's have a look at silver. You've got Ag and then 1 electron Ag plus 1 electron Ag. So at one half reaction, that's where Ag will lose electrons, Ag plus an electron. And then your reduction half reaction, you've got Ag plus receiving electron to form Ag. So what you want to do is you want to make sure that in the solution you always have the silver ion. That is why the oxidation has to take place, where your silver electrode will erode and give electrons and then dissolve into the solution. As it dissolves into the solution, the spoon gets covered with silver metal. So your spoon ends up being silver. All right. So the questions that are asked in this in this question, in this topic, are related to why is it important for you? If you look at the ship, why can't you cover the ship with certain metal, but you can cover it with certain metal? And then if you look at the ship, is made from iron, and then if you choose the metal where iron will be oxidation half reaction, it means your ship will have holes, and then in a long time this ship will sink. So we cover it with another metal to make sure that the iron is protected. Okay, so that is the electrolytic and the galvanic. So let's check what is it that we still have to do. We still have to look at the relationship between current and potential difference to the rate and the equilibrium. So this is where we're calculating the E cell, and then with the equation that I gave you. So from there you must understand the process of redox reaction that takes place in the galvanic cell. That's the movement of ions in the solution and the direction of electrons in the external circuit, as I've shown you when I was showing you the two beakers. And then the function of the salt bridge, we've also mentioned that one must also be able to state the function of the salt bridge. It completes the circuit. It helps with the migration of ions. Okay, and then you must also be able to write the cell notation. So for the cell notation, that is only applicable for the galvanic cell, not for the electrolytic cell. So let us look at the reaction that we had here, where we had copper reacting with zinc. So for our cell notation, there is a handout that came out last year in terms of the mistakes that learners are doing when we mark the exam. Please ask your teacher to provide you with that so that we don't do the same mistakes again. So when you write the salt bridge, the cell notation, all right? How do you write the cell notation? On this side you have your oxidation, followed by salt bridge, and then your reduction half reaction. Okay, so if you look at our half reactions, you've got zinc giving electrons to form zinc ion. So our cell notation in this case will be Zn forming Zn2 plus. All right, and then it's important to indicate that this condition will happen when this solution is 1 mole per cubic decimeter. So the concentration of the solution has to be 1 mole per cubic decimeter. And then, okay, this is our oxidation, zinc changing to zinc ion, and then followed by a salt bridge. So the double line indicates the salt bridge, and then on the other side you'll have a Cu2 plus forming Cu. So the condition 1 mole per cubic decimeter. All right. So it is Cu plus forming Cu. That's for your reduction, and then Zn forming Zn2 plus. All right. So this is how you write your cell notation. Okay. Zinc ion, salt bridge, copper ion, copper. All right. So these are easy marks to just write this, and then you get your 3 marks for that, for the salt bridge, and also for the reduction half reaction. Okay. So that is what they say you must be able to do, that is to write the cell notation. Then you say you must also be able to predict in which reduction, predict the half cell in which the reduction will take place when 2 half cells are connected. Just like we have done with the copper and zinc electrode, what you do is you make use of the table for the galvanic cell, and then the table will help you to predict which half reaction is reduction and which half reaction is oxidation. And then making use of the standard electrode potential table to do the calculations. I've just shown you how to do that. All right. And then the other thing that you must also be able to do is understanding the process of redox reaction taking place in electrolytic cell. That just describe the movement of ions. Okay, we talked about that state in which the reaction. We also talked about that. Write down the overall cell reaction, your oxidation half reaction, reduction half reaction, and then you combine the two, you remove the electrons, and then you have your overall cell reaction. Okay, and then describe the using the half reaction and equation of the overall cell reaction, as well as the layout of the particular cell using the schematic diagram. The following electrolytic process, the decomposition of copper chloride. I've just shown you the decomposition of copper chloride by the. So this is the decomposition of copper chloride, where the chloride ion will give you electrons, and then copper will receive the electrons to form copper solid. All right. So this is what they are talking about when they talk about the decomposition of copper chloride. Electroplating, the plating of the spoon with silver or nickel. Refining of copper. So the refining of copper is similar to the one that we talked about, the composition of copper chloride. So for the refining of copper, what happens is you've got your copper with the ore, and then you will connect the copper electrode on one end, and then the other end you can connect the other copper electrode, or you can connect the carbon rod. So on the electrode that is connected to the negative terminal, the copper will compile on that electrode as you are purifying it. And then electrolysis of the concentrated solution of sodium chloride, and it is used in the chloralkali industry, the recovery of aluminum metal from bauxite that we get from Australia, and also describing the risk and the environmental hazard that are involved or that are related to the electrolytic process using industrially. That is the production of chlorine that in the chloralkali industry, and the recovery of aluminum in, from bauxite. All right. So when we come back from break, what we are going to do is I'm going to explain to you quickly the chloralkali industry, and then from there I will quickly show you one or two problems from the past paper, and then after we are done, the second part of this, I want to spend more on the fertilizer, showing you what the process that is taking place industrially and the fertilizers that are formed, and the role of the fertilizers in plants and also in human beings. So we'll meet each other after break. For now, just go out and stretch your legs and come back after break.